Hello everyone, I am Zach Peterson. Welcome back to my channel. Today we're going to be talking about electronics and PCBs with multiple antennas. Now this topic came from a viewer question on one of my short videos, and of course if you leave a great question in the comment section on this channel, it might just end up in one of these videos. So let's go ahead and jump in and get started talking about multi-antenna PCBs. Now before we get started, let's take a quick look at that viewer question. Hanafi writes, hello, we need a video talking about the considerations for a multi-antenna PCB. Well, I'm happy to talk about PCBs with multiple antennas because I've done quite a few systems that use multiple antennas, but how you go about using those multiple antennas really depends on your overall system architecture and what you're trying to do. Some of the things in the PCB layout are going to be the same no matter what your system architecture is, but how you do the routing and how you plan out or floor plan your design could vary depending on what type of system you're trying to build. So first, let's go ahead and jump on the whiteboard. We'll run over some system architecture examples and what you can do or how to incorporate multiple antennas into a single device. And then I'll show you a couple examples in Altium. We can learn a little bit more about how to use multiple antennas in a PCB. So first, let's take a look at the different types of systems where you might use multiple antennas on a PCB. I think the most common type is where you basically have two chips. We'll call them chip 1 and we'll call this one chip 2. And with these two chips, each have their own separate RF interface, and so the result is that they each have their own separate antennas. So we have chip 1 that has its own antenna, and then we have chip 2 that has its own antenna. And typically they're not operating at the same frequency. So for example, this one could be at 2.4 gigahertz, and then maybe this one is at, for example, sub gigahertz. Or another common example that I've dealt with is, for example, GPS/GNSS, this type of system. So you basically have a 2.4 gigahertz interface and then some other protocol that you need to access over an antenna. And in this case, they're totally operating at different frequencies, and you may even have different antenna structures. So for example, this one could be, let's say, a printed antenna, and this one could be, for example, maybe a ceramic antenna. Or maybe it could be a module, so maybe it connects with like a small coax cable. Now in these systems, because we don't have any coexistence in the same frequency bands, we basically have these two antennas operating totally independently of one another. So this one is going to receive and transmit on a single antenna, and this one is going to receive and transmit on its own antenna. So we don't have any risk that, for example, this signal coming into this antenna gets received by chip 1 and then messes with any of the reading of the 2.4 gigahertz signal that needs to be read by chip 1, and vice versa. So they're essentially totally independent of each other. Now, in terms of what we do on the PCB layout is actually pretty simple. We would basically just separate these and put these somewhere along the board edge where they're not going to be interfered with any digital signals. So for example, we could have, let's say, chip 1 located here, and then it goes out to, let's say, a inverted F antenna, and this is located along one edge of the board. Then we have our chip 2 located elsewhere on the board. Maybe it's located here. Draw in chip 2, and then maybe this comes out to, let's say, a U.FL connector and then connects to a module. Some simple examples here. So we've basically separated our RF stuff away from our digital stuff. Maybe, for example, you have an MCU somewhere in here that communicates with these two chips, or one of these interfaces is maybe built into your MCU. All of these options are possible. I think the main guideline here is to figure out which edge you want the antennas located on, because it doesn't really make sense to put your inverted F antenna right here in the center of the board, and it also doesn't usually make sense to put your antenna, maybe like a ceramic antenna for chip 2, also in the center of the board. So I prefer to put these antennas somewhere located close to the edge. Another reason that you want to do that is because, for example, if you have a printed antenna, you're going to have to put a ground cutout, assuming that this is meant to be an omnidirectional antenna. So we want to have this ground cutout here. And by putting this ground cutout somewhere in the corner of the board or along the edge of the board, it's not going to interfere with any of the other routing in the board, and it doesn't take up any of that real estate for example, your digital signals. So in this example, we were looking at two chips operating with totally independent frequencies. But what if we have, for example, coexistence? So for example, we have two different chips operating in or almost near the same frequency band. Well, in that case, we may need to have chip 1 connected to its feed line through an antenna switch. And then this connects to our antenna. And then same thing for chip 2. With chip 2, it also might need to connect to its feed line through an antenna switch. And then you would need to have your host processor toggle which of these switches is active so that you're only receiving and transmitting on one of these antennas at any given time. So you're basically going to have an MCU that implements time division multiplexing. So you're basically manually switching and toggling when each of these chips is active and transmitting over its own antenna. Now, in terms of the PCB layout, where should we put all of these antennas? Well, I think this is pretty simple because here we can basically do the same thing that we saw earlier where we had the two chips transmitting on different frequencies. Here, if both of these are transmitting at, let's say, 2.4 gigahertz and 2.4 gigahertz, we can still have the same PCB layout, but we need to make sure that we put these antenna switches somewhere where they can be accessed by a GPIO from the MCU. This way the MCU can toggle which of those switches is active at any given time, and then you won't have issues with chip 1 receiving and interpreting a signal that was instead meant for chip 2, for example. Now, what if we want to have a system where we're able to select between two different antennas? How would we set that up? Well, typically when we do that, we would want to use an antenna switch, but instead of having a single pole, single throw switch, we would have an antenna switch that switches between these two antennas like you see here. So we would have our antenna switch, basically works like this. We would have our chip here that is going to be doing the transmitting and receiving. And then again, we would have an MCU that then routes through a GPIO over to this chip and then over to the antenna switch to then select between which antenna we want to use. So I'm actually working on a project that we'll look at momentarily that takes this approach where the user can then select which of the different types of antennas they want to use. So this could be, for example, a printed or a ceramic antenna. And then this could, for example, be a U.FL connector that then goes to an antenna module that you would purchase off the shelf. So this lets the user have some flexibility as far as which type of antenna they want to use in different applications. Now, what if we want to do the inverse of this, where we have multiple frequencies, but we want to consolidate them onto a single antenna? That way we don't spend all of this room on the PCB taking up multiple antennas. How would we do that? Well, there's a more elaborate solution that you can implement with a diplexer, and I talked about this solution in a webinar that I gave for CLIS last year. Let's jump onto the computer and take a look at some slides, and we can see how to implement the diplexer and antenna switch solution. So here's one example where we can use a diplexer to interface two different frequencies to the same antenna. And essentially the diplexer ensures that one frequency only routes to a single output, as you can see here in this block diagram. So we have our host microcontroller that controls the system and then determines when this NRF 7002 chip is going to broadcast, and then those two signals run to the same antenna. And this has to be a dual band antenna that's capable of broadcasting and receiving at both of these frequencies. Now, what if we have another chip that also wants to broadcast at one of these frequencies? Well, here, for example, we can implement time division multiplexing if our microcontroller also has an antenna interface like you see here. So here's an example with the NRF 5340. And the NRF 5340 also has an RF interface, which is typical of most of the NRF series microcontrollers, and it can broadcast and receive on its own antenna. So here, the NRF 5340 would need to control when the NRF 7002 is active and broadcasting or receiving. And it would do that through these IOs that you see here drawn in the block diagram. Now, the NRF 7002 can still use this diplexer solution, but it would essentially just be turned off. So now the NRF 53 is implementing essentially time division multiplexing, as I described earlier. Now, we can get this more elaborate if we like by implementing a switch, and that allows us to consolidate down to a single antenna like you see here. So I think the antenna switch control is a little better to use because here you don't have to fully turn off the NRF 7002 in order to control when the 2.4 gigahertz interface is broadcasting or receiving, and it still allows the 5 gigahertz interface to broadcast and receive as needed. So here in this architecture, you're using the antenna switch to actively switch between the coexisting 2.4 gigahertz protocols, as you can see in the block diagram. And then you use the diplexer to then choose whether the 2.4 gigahertz interface or the 5 gigahertz interface gets to broadcast over this antenna. Now let's take a look at another example. Here we have another example where we're using a switch, but this switch has 3 inputs and 1 output to the antenna. So here we're switching between 3 different interfaces actively using a switch control, which is controlled by one of the IOs on one of these 2 chips. So you can have the microcontroller run the control, or you can have the NRF 7002 run the control. But in this example, we're basically switching between the 2.4 gigahertz interface on either of these 2 chips, or we can use the 5 gigahertz interface. And this allows us to implement full time division multiplexing across all 3 of these interfaces. Now what I want to do is take a look at the NRF 52 project I'm working on, which implements the system architecture that you can see here behind me on the whiteboard. We'll also look at a Texas Instruments reference design, which shows a phased array, and that is a good example that shows how to use multiple patch antennas in a PCB. So here on screen, I have the NRF 52 package project that I've been working on, and this project was originally inspired by the microcontroller module teardown video that I did on Altium Academy. I decided to take the same design approach for a package with the NRF 52 chip scale microcontroller. And as you can see here on screen, we have the microcontroller in a BGA package. It has very fine pitch BGA. And then you can see here we have some other peripherals that are integrated underneath a shield directly mounted on the board. Now in this design, we have our feed line connecting directly to a matching network, and then that matching network connects to an antenna switch. Now this antenna switch is controlled with one of the GPIOs from the microcontroller, and then the outputs from that antenna switch connect to 2 possible antennas up here on the top side. So you can see here we have a UFL connector that connects to an external antenna module, and then we have a ceramic antenna here in the upper left. So how should we route the feed lines coming out from this design? Well, of course, we have to look at the stack up and figure out the 50 ohm impedance width for these feed lines. Once that's set in the design rules, you can then just select one of these pins to route and make sure you have the right width set here in the properties panel. And then we can just route these traces over to the inputs on the antenna components. So that's pretty simple. You can see here I'm using curved traces and then just routing them in between the gaps in these ground pads for the shield that sits on top of the board. Now with these antenna feed lines, we would also want to make sure that we apply coplanar waveguide routing. So we would want to then fill this in with a polygon and then apply stitching vias along the length of these traces. That's going to ensure electromagnetic field confinement around this trace, and it's going to ensure that there is high shielding effectiveness around these lines carrying that 2.4 gigahertz signal. Let's take a look at that reference design from Texas Instruments, because this shows another way that antennas are being increasingly used on millimeter wave sensors. Now this particular reference design is for a radar module, and you can see here that we have 2 sets of antennas. Here we have 3 antennas located on the lower half of this design, and then here on the right side we have 4 antennas that are all grouped together. Now if we put this into 2D, we can see what these antennas are being used for. We can see that this array of antennas over here is the receive side array, and then this array over here is the transmit side array. So here, these antennas are all placed in a very specific group that allows directional broadcasting and reception of an electromagnetic wave at very high frequencies into this antenna array. So you can see here that to maintain a specific phase relationship across all of these antennas, length tuning is essentially implemented across all 4 of these feed lines. You can see that there is a little bit of length tuning enforced here, but not with the traditional length tuning structure. But these are routed such that they have the same lengths from the output of the RFIC over to these antennas. Now, I mentioned earlier that when we align these antennas up near the edge or in the corner of the board, that we want to make sure that there is ground cut out below those antennas. But in this particular type of design with multiple antennas, we actually need the ground because these are not omnidirectional antennas. They are only broadcasting and receiving along a specific direction with respect to the top surface of this PCB. Now, we can also see in this design that we are using coplanar waveguide routing because of this via fence that we have in the grounded polygon on the top layer. The clearance to these feed lines is very specific. It is designed to ensure that we have controlled impedance on this top layer for these feed lines, targeting a 50 ohm impedance. Now you can also see here that this via fence is formed with blind vias. Now that's really important because then these vias won't take up any space on the inner layers, and you can still use those blind vias to define the via fence for these coplanar waveguides. So this is actually an approach that is very commonly used on the Texas Instruments radar module reference designs, and I'm definitely going to be using it here on this NRF52 package design. That way those feed lines won't have a bunch of vias that take up space for routing on the internal layers. So if you want to see how this package design turns out, make sure to hit the subscribe button. You'll be able to keep up with this project as I get it finished. Thanks everyone for watching this video, and of course, thank you for the awesome viewer question. And if you have a great question, leave it in the comments section and it just might end up in one of these videos. Make sure to hit that subscribe button, hit the like button, and we'll see you next time. Thanks everybody.